First off, welcome everyone. Good afternoon or good morning, depending on where you're connecting from. And welcome to the next talk in the NSSC Alumni Speaker Series. And today we're pleased to welcome Krystin Stiefel from ORNL. So she received her undergraduate degree in chemistry from Adrian College in 2012. And after that, she actually joined us at Michigan State University and worked with us for a little bit on measuring fragments and neutrons produced in fragmentation reactions at the National Superconducting Cyclotron Lab. And she graduated from MSU in 2018 and then decided to go further south, get away from the snow, and is now at Oak Ridge National Lab, where she is an experiment safety engineer at the Oak Ridge National Lab's High Flux Isotope Reactor. And she's going to talk to us a little bit about working with different research groups in isotope production and materials tests. And so with that, I'm going to turn it over to you.
All right, thanks, Sean. So like Sean said, I'm Krystin. The title of my talk is Safely Running InVessel and Gamma Facility Experiments at HFIR. We say HFIR, I know it's very confusing to look at the HFIR, but it stands for High Flux Isotope Reactor. So HFIR makes sense. So I'm really excited to talk to you today about my work and some of the projects that I'm involved in and all of the collaborations that I work with, because I don't work in one specific research group. I work with all kinds of groups in coordinating all of their experiments and their projects that they have to do. First, and I know Sean just gave me an intro, but I figured I would go a little bit over my path to ORNL. And there's a theme to this talk, which is your past will always come back to you in some way or another. All of these kinds of people and places that I've been to in the past end up haunting me, even now, in all of the collaborations that I work with. So I grew up in Monroe, Michigan. And if you pull out your handy dandy Michigan map of your hand, that's located right here, just north of Ohio. And this is the home of the Fermi 2 nuclear power plant, pictured in the top left of this of the slide. My mom worked at this plant. She didn't work in the science side of things. She works with like money and projects and project management and all of that kind of thing. But that meant that once in a while, when I was little, pre 9/11, I got to go in to work with her, which to me, as like a 5-year-old, I would color a lot of highlighter pictures that she had with the highlighters at her desk. So my elementary school also did field trips to Fermi, including one memorable time when we got to go into the middle of one of the cooling towers and ruin all of our sneakers for the next 5 days due to all of the moisture that we picked up in running around in the ponds down there. But the point is that I grew up around the nuclear topics, so I was never really afraid of them. And that kind of just sat in the background of my head the entire time that I was in education. But I want to point out that it wasn't really a linear path, and I've never like always wanted to be a nuclear science researcher. It's just been in my past. I went to Adrian College, like Sean said. It's a very small liberal arts college. There's less than 2,000 students there, and it's located in Adrian, Michigan, which is a very small farm town with lots of cows and corn. And I was thinking at the time I was going to do pre-medicine, but it turned out I didn't really like the biology side of things. But what I did like was chemistry and physics and the very, very tiny amount of nuclear science we got from either of those topics. And I also liked lighting my hand on fire, as you can see that. And I swear, I know I'm a safety engineer now, I swear this is safe. It's just methane bubbles and you soap up your arm and it's totally fine. It's totally safe. So don't worry about that. So while I was there, during a few summers, I actually tried my hand at working at Fermi 2 for a while over the summers, going in and doing document control and document changes, drawing design changes. Basically, my intro to engineering is what I'm saying. So I'm picking up chemistry stuff from Adrian College. I'm picking up engineering from Fermi 2. Thankfully, one of my professors at Adrian College knew about this nuclear chemistry summer school that was offered at San Jose State University. So I got to go out there for 6 weeks and learn about different topics, including like radiochemistry and forensics and nuclear fuel. And funnily enough, Eva Uribe, who was one of your earlier speakers, I believe, in this series, she was my roommate at this. So again, the past always comes back because nuclear is a very small field and you will run into the same people many, many times. At this San Jose State University Nuclear Chemistry Summer School, that's also where I met Paul Mantica for the first time from Michigan State University. And so he was kind of what led me to going into Michigan State, with seeing the work that they do there. Like Sean said, I went to Michigan State University. My thesis was titled Measurement and Modeling of Fragments and Neutrons Produced from Projectile Fragmentation Reactions, which basically meant I took some beams and I threw them on a target and tried to measure all of the pieces that came out using a series of detectors, including in this photo, I believe that's Lisa, it's the Mona Lisa detector. It's a modular neutron array and large area multi-institutional scintillator array. So it's just a series of neutron detectors. And so I spent quite a few years there working on my dissertation project. But while I was at MSU, I was also part of the NSSC. And that was really great because it gave me so many opportunities. And I urge all of you who are involved with the NSSC to take advantage of those opportunities. So like, for example, we got to go visit national laboratories as part of that program. So I know we went to Los Alamos one year and also Lawrence Livermore as well, and got to talk with the researchers there and learn about all of the projects that they work on, all of the research that they do, and lab tours. Lab tours are always fun. So we get to see things in person, not just, through pictures. So hopefully those can come back eventually in some way in the future after all of this. So those were really great. NSSC also involved a lot of workshops and conferences. So that was also a great opportunity to go learn what other people were doing within the consortium and also network in general and meet a bunch of people, including people who I work with. So I think this photo at the bottom is from the 2017 workshop. I don't remember exactly, but I think that's the year it's from, and I'm in there somewhere. So since I was tied to the NSSC, I also learned about this public policy nuclear threats boot camp in 2016 that I attended, and that had like lectures and discussions and debates and political policy simulations on nuclear policy, which wasn't really something that we covered as part of my graduate work. As you know, that wasn't part of my research, so it was a nice supplementary thing. And learning about the policy side is, I think, very useful, even if you are strictly research for the most part. And since now I'm at ORNL, I figured I'd highlight a few of the connections that I've had directly with ORNL. In 2013, or 2014, sorry, I spent a week at ORNL doing the exotic beam summer school, where again, I met people who I would later work with. So it was another networking experience. And there were all these other networking events that allowed me to meet Oak Ridge employees, which I'll bring up a few later. So with all of this national lab experience or ability to go see national labs, it's not really a surprise that I ended up at one. This is a great photo of me in some of my fun gear. So back in December 2018, I started work as an experiment safety engineer at HFIR. My main goals as part of this group is to maintain the safety of experiments in the reactor and coordinate InVessel and gamma facility experiments. And to be honest, this isn't what I normally wear. Normally, I'm much more of an office environment person. But occasionally I get to go out to the reactor pool bay and look at some things, and I get to wear all of these lovely scrubs and gloves and booties. And this isn't even like the full attire. If I'm up at the actual railing by the pool, I get to wear the full bunny suit. This is from a different project that involved, quote unquote, the clean side of the bay. So I didn't have to dress up as hardcore. I jokingly tell my family that I make sure that the experiments don't blow up the reactor and the reactor doesn't blow up the experiments. But really, I just aim to compromise that I try to make sure that the reactor is not compromised in any way. So compromising the reactor could lead to delays for fixing it, reduced output, or even full shutdowns which would affect all of the work, not only that I deal with, but the work that other experimenters deal with it, who I don't even collaborate with. So associated neutron scattering facilities are a big part of HFIR. And that can be really detrimental to all of these programs and their milestones. And it can even limit the ability to produce very important isotopes, such as like for cancer treatment. So we really don't want that. We don't want to compromise the reactor. We want to make sure everything is okay. And of course, there's also the human aspects related to safety. We need to make sure that no one gets injured in an accident, or that they're exposed to radiation. That's a pretty big deal. But I'm getting a little bit ahead of myself. So let's take a step back and just talk about HFIR for a second. So why build HFIR, or this research reactor? So the reactor that I work at, HFIR, is rooted in a call from Glenn Seaborg in a letter to the US Atomic Energy Commission chairman at the time, Lewis Strauss, in 1957. And he wrote, "The field of new transuranium elements is entering an era where the participating scientists in this country cannot go much further without some unified national effort. The future progress in this area depends on substantial weighable quantities, say milligrams, of berkelium, californium, and einsteinium." So one great way to generate all of these elements is to use a research reactor, specifically a research reactor that generates a very high flux of neutrons, which is HFIR. So like I mentioned before, HFIR stands for High Flux Isotope Reactor. This is a picture of the building of HFIR at Oak Ridge. It hasn't changed much, at least in the 2 years that I've been here, or this time this photo was taken probably a decade ago. The building remains pretty much the same. HFIR was completed in 1965 in order to meet this national need for the production of these transuranic isotopes. And it provides a peak thermal flux of 2.5 times 10 to the 15 neutrons per square centimeter per second. So it's very high. It's one of the highest in the world. There's another reactor in Russia that is around that same range. But I believe everything else is less. Today, HFIR is more known for its neutron scattering programs. And the neutron scattering facilities at HFIR contain this whole suite, this world-class collection of instruments used for fundamental and applied research on the structure and dynamics of different kinds of matter. I don't deal with that. I have been through the beamline room a few times, but I don't deal with neutron scattering. I don't want to mess up their projects, so I make sure that the reactor is running okay, but I don't touch the neutron scattering. So a few reactor characteristics that we have. The fuel that we use, and I'll talk a little bit more about the fuel in a second. The fuel that we use is an aluminum-clad uranium oxide plates, not pellets, but plates, with a total of just over 9 kilograms worth of uranium-235. And then our core is encased within a beryllium reflector, which is then placed into a pressure vessel made of carbon steel with stainless steel cladding. We run, unlike power plant reactors, which run pretty constantly for a year to 18 months, we only run our fuel for 23 to 26 days at an 85 megawatt operation level. The exact amount of how long we run depends on what is currently in the reactor. We try to stay for 26 days because generally the neutron scattering people want us to make sure that we are running as long as possible so they can get the neutrons for their projects. But depending on what we have in the reactor, it could reduce that level. And I'll talk a little bit about that later. And we aim to operate about 6 cycles a year, depending on what's going on with different maintenance tasks that are happening. So starting off in the very center of the reactor, at the very center is this target basket, which is in this photo. It's the very center area. You can see the fuel plates around it. I'll chat about them in a second. This target basket is about 5 to 6 inches into 5.5 inches in diameter. So this is really a photo of a model of our target basket and a model of our fuel. It's not the real thing itself. And the cylinders that are popping up out of the center are our targets or models of our targets, which would contain the experiments that we're putting inside the center area or the flux trap. So HFIR is based on this flux trap principle. in which the reactor core consists of the cylinder of fuel surrounding this unfueled region, or the island, or the flux trap where these targets are. And the configuration helps to allow fast neutrons from the fuel to be moderated and sent into the island, which creates a region with very high thermal neutron flux at the very center, or in the center of the flux trap. So surrounding that, the flux trap is our fuel element. And it's actually a two-part fuel element. It's a unique fuel design with this inner region and this outer region. So this is a photo that shows a model, again, of our fuel with the flux trap removed from it. And so you can kind of see, based on that person's hand in the corner, you can kind of just see how big this is. The full assembly is only about 2 feet tall by about 15 inches wide in diameter. So it's actually pretty small. At least it seems small to some people who have taken tours on. So our inner fuel element contains 171 plates, and our outer fuel element contains 369. And all of these plates consist of this uranium oxide aluminum dispersion fuel, which is highly enriched, actually. It's about a 93% enrichment, an aluminum-based filler, and an aluminum cladding. And then each plate is only about 0.05 inches thick, or thin. They're pretty thin, and they're uniformly distributed in order to make uniform coolant channels for our fuel. So yeah, flux trap goes in the center of that, fuel goes around, and then we take this whole thing and we stick it in our beryllium reflector. So the beryllium reflector is about 1 foot thick, and it acts to moderate the neutrons. The reflector contains spaces for more experiments. So not only can we put experiments into the center where the flux trap is, but we can also shove them into the beryllium reflector. Specifically, these reflector spots are subject to a lower flux of neutron and gamma rates. So we generally use these for plutonium-238 production and fuels testing, and a lot of other things, anything that requires a lower amount. The beryllium reflector also contains these beam tubes. You can see them in the left picture, these holes that are on the side, and those allow neutrons to escape or to be beamed out into experiments outside the reactor shielding for the neutron scattering experiments. We actually have to change these out periodically, the beryllium reflector. We have to change them out periodically because of internal stresses that are caused by swelling. And we're coming up on one in 2024. So my group or a member of my group and other people at the lab are working already to get prepped and ready for that, because we have to plan things out on a long scale. So altogether, this is a picture of the full-on thing, where we have the target bundle sitting in the center, filled with holders containing experiments, surrounded by the inner fuel elements, which is then surrounded by the beryllium reflector with the holes that contain other experiments. So we can do a lot of different kinds of experimental work just within this vessel, so ignoring all the neutron scattering stuff. This is a cartoon that we use to kind of just give an easy view of like what possible options we have at High FIR for the InVessel. You can see on this that the reactor has these 4 horizontal beam tubes. They're labeled as HB1, 2, 3, and 4. Those are for the neutron scattering. Those are the neutron scattering tubes, and they get sent out to their own beamline facilities. So out in the permanent beryllium, which is that green area, we have these 22 spaces called the VXFs, or vertical experiment facilities. 16 of them are small and the rest are large, as you can see from the diagram. And each of these facilities has a permanent aluminum liner, and normally non-instrumented experiments are irradiated in these facilities. Although we do have one, it's VXF7, that's dedicated to one of the pneumatic irradiation facilities that supports the neutron activation analysis lab. So that one I don't deal with as much. And it's unavailable for other use. But the other holes are available for my experimenters to use. And so when they're not in use, we'll plug them up with like a beryllium or aluminum plug or some kind of flow regulating orifice and no plug. In the center area, we have this flux trap. So that, that is the central area that I was talking about before, with all of these holders and the experiments, and they're gridded out in a way for us to identify them. The 6 orange circles that are around the center, those are what we call peripheral target positions, or PTPs. And those are experiments located at the outer radial edge of the flux trap. And the fast neutron fluxes in these positions are actually the highest available to the experimenters. But there is a very steep radial gradient as you move from the center line. So we can actually have experimenters who require us to orient things very specifically within a holder in order to make sure that they're getting what they need. So we're able to load up 9 targets, and I'll show, you can see a photo or rendering of one of these targets here on the right corner. That's an example of one of our little targets. They're about 2 inches long, and they're filled with some material to either generate isotopes or some kind of material to test for under irradiation conditions. And these are called capsules. We sometimes call them rabbits, and that's due to some terminology involved with a later project that I'll deal with, where we shoot them through tubes like rabbits going down a rabbit tunnel, a rabbit hole. So, you know, if I use capsule or rabbit interchangeably, that's what I'm referring to. So each of these holders and the PTPs can handle 9 targets at once. And then within the areas of the little hexagons, there are 31 target positions that are available in the flux trap for these hexagons. And these are called target rod rabbit holders. These positions were originally designed to be occupied by full target rods, so entire things to take up that entire vertical position, in order to create these trans-uranium transplutonic elements. However, we can irradiate other experiments now because other holders have been designed, so we can go back and irradiate these little tiny 2-inch rabbits in these as well. So it's a variety of options. They can choose a target that is an entire rod, filling up that entire position, or if they only need a small section, they have these 2-inch options that they can use. And we can put 9 of those as well in each of those target holders. The rabbit or capsule design for both the PTP and the target holders are pretty identical, which is actually really useful because it helps to simplify the designs, which means it helps to save on costs, and it also just provides some more irradiation options. So if something really has to go in for a certain cycle, it could go in either of these kinds of holders. So experiments loaded into any of these targets or any of these points, vessel points, can be irradiated for as short as 1 cycle, which again is like 23 to 26 days, or as long as well, the longest that I've seen requested is 100 cycles. And again, we run about 6 cycles a year. So if you can extrapolate that out, so a fairly long amount of time, you know, maybe by the time I retire, we'll be pulling some of them out. And there are some that have been sitting in there for quite a few years as well. These are a lot of like materials testing. They really want to see what long-term radiation exposure does to that. But usually targets aren't irradiated for 100 cycles. They're normally in like the 10 and under range, just because that's what the project deals with. That's great if you can handle a full cycle, but some experiments that we run actually cannot be in there for the entire time. And so if they don't need as much exposure to the neutrons, we have something called the hydraulic tube facility, which is the red spot in the center, labeled HT. So this is useful for experimenters who want the high neutron flux without committing to an entire operating cycle. And it's ideal for the production of things like short life medical isotopes, where they have to get things out and shipped fairly quickly, or for irradiating materials at smaller levels of irradiation. So some of our materials groups will come in and have a series of different kind of capsules where they'll say, well, I want this one irradiated for 5 days, and I want this one irradiated for 10 days. And so this is able to provide that kind of capability for that. So The targets we place in here are very similar to the style of the individual 2-inch targets from before. And in fact, there are some cases where we have put targets into the hydraulic tube that were in the flux trap, the rest of the flux trap, or vice versa. It really just depends on what's going on and what the experimenter needs. And hypothetically, we can load 9 at once. That generally doesn't happen. I'll talk about why in a second. And so in this photo shows the core, and you can see the pipe that comes out from the center that goes into the hydraulic tube facility. This is where the term rabbit name comes from, because the capsules are shot into it. And it's great too when they pull them out, depending on how long they've been in there and what the material is, they'll come out and they glow this really nice blue as they travel across the line. So you can see it shoot out from the core into the storage area. So with all of these possibilities, this kind of begs the question of like, how do we prepare and qualify all these experiments? Because it's obviously not something where you just show up to my office and you're like, hey, I have this, can you throw it into the reactor? It's usually not like that. So how do you run a flux trap experiment? Or so you want to nuke some samples. So what happens is an experimenter or a user will propose an experiment or project that they want to do. And my group will work to run a feasibility screening. It's a very basic level of like, can we actually do this? So this is kind of based on like historical things that we've done with the reactor. Have we done something like this before? Is it similar to something we've done this before? Is this completely nuts? Like, can we just not do this at all for whatever reason? Because sometimes it turns out that what they're asking for doesn't actually fit us. We've had cases where it would take too long for them. And I said like we can run things for hundreds of cycles, but you know, there's sometimes limits to what they can actually, how long their grant lasts. Sometimes it's too much flux, so they underestimated the capability of HFIR. Sometimes it's, we know of a different facility that we can use for them. So for example, this is a really high flux neutron environment within the vessel. If they're looking for something like a gamma field, then that's a different facility that we have. And so we can direct them to that, which I also deal with, so it's very useful. I can direct them just to me. But they can always revise the concept depending on what it is. Maybe they still really want something similar. And generally we try to work with these experimenters in order to figure something out. We want to try to make them all as happy as possible. So once we think we can actually pass on the feasibility, say, yes, this is going to work. How do we actually, what we have to do now is determine if it's already covered by an existing document. So we have these things called EABDs, or experiment authorization basis documents, and these guides contain limits to what we've determined to be safe given certain conditions of the reactor. So if an experiment is already covered in these, they just have to actually build the package, build the rabbit, build the package, send it to us. We go through it with QA personnel in order to make sure that they actually meet all the requirements of these documents. And then assuming it's all good and a mistake hasn't been made, we will accept the experiments and work to schedule it into our reactor. And we work out a run plan. But if an experiment isn't covered by a current document, actually just take a step back. So a lot of our experiments that are covered by existing authorization documents are things that we run pretty constantly. We make a lot of medical isotopes over and over again. And so they're a pretty constant thing. We already have those going. So we're able to just use the current documentation for it. And that's a pretty straightforward process. But occasionally, or rather often, actually, we get new things that are not covered by the documents. And so that's where we get into some really fun stuff. So there are generally 3 types of ways that we can deal with new experiments that we haven't seen before. So if the change is something small, and a one-off, we can write something called a deviation. And it's really a one-time thing. We actually just wrote a deviation recently because the experiment authorization document mentions something, it doesn't mention anything about cycle limitations. And it turns out that this specific kind of rabbit is actually limited to a certain number of cycles. And so we wrote a deviation just saying like, hey, by the way, we can't put this in past 23 cycles, I believe it was. We're only scheduled for 8. but we can't put it past 23. So everyone make sure that we don't put it past 23. And so that was a deviation example. And we literally just did that last month. If it's something that is very similar to a current document, we could revise that document. So for example, if a target has been previously qualified for use in the target holder, but they now want to install it in the PTP or use it in the hydraulic tube, that might just involve revising the current document. Or it could be brand new. So for example, we get a new material that is not covered by any of our current stuff. That creates brand new stuff. And so that will involve documentation of the change, running calculations to ensure the capsule will be fine, making sure that it's not going to cause damage to the reactor if it were to crack open, or just make sure it doesn't crack open in the first place. So there's calculations involved, and just lots of modeling and trying to figure out how it will act within the reactor. So then we write these new documents, we take a look at them and make sure that everything is documented. And once that's done, they can now build their rabbit, build their target, and send it to us. And we go through it with the QA personnel and we make sure all of the requirements are met. And assuming that they meet the requirements and no one has messed up too badly, then the experiment is accepted and we work out a run plan. So it's easy, right? That's fine. Okay, so some of the points that we have to consider, and these are just a few things, are listed here. So for target design, we actually have to maintain flow, and depending on the type of target we use, we can have issues with targets locking into place and rubbing against each other, which can create capsule failure, and we really try to avoid that. And so that comes down to capsule design and also placement of the capsules within the reactor. There are some capsules that have this issue that we cannot avoid, and so we have to make sure that they are surrounded by safe things in order to make sure that they do not rupture any other capsules within the reactor. There are also holder design considerations. We're actually working to remodel them right now in order to make them easier to replace, making sure that when they bend, we can replace them more easily. There's the length of irradiation. So if something has to be kept within a certain time limit, like I mentioned, that deviation from before that we just did, or if it's a really long irradiation that's impractical, how can we fix that? Although to be fair, again, we've had capsules that are scheduled to irradiate for over a decade. So it's more about the timeline of the experimenters and their funding. There are space considerations. It's all well and good that you want to come in with a bunch of targets to take up half the reactor, but that's not really practical for the rest of the program. So we have to coordinate with everyone else. There are neutron poison considerations. So is this material going into the reactor going to be an absorber? And if it's an absorber, it can actually shorten the reactor cycle, which affects not only the experiments that are in the reactor InVessel, but also all the neutron scattering crowd, and they do not like that. So we have to make sure that we, any neutron poisons that we would put in are very limited, because we do not want to shorten the cycle as much as possible. There could be physical changes to the material. So for example, if something expands, can it rupture the capsule, or is it gonna, or like, is there enough room for it to expand if it does expand? Or samples that could melt. And of course, there are like the produced products, like if this is something that we have, is this something we have to store for a long time in the pool before we can send it off for them to work with? Or are there issues with the byproducts that we have to be aware of that could cause problems? We also really consider these unlikely events. So for example, we really try to make sure that capsule failure doesn't happen at all through the design and through various testing, like leak tests, and making sure that we place them appropriately within the reactor. But we do need to consider the idea that something could still fail. And so, if a capsule should break, what happens to the material inside of it? Could it plug up anything and reduce the flow? Or potentially worse, is it something that will react with the water? So there's a lot of risk analysis we have to play. Something could be low risk if it's really common or something to deal with, or something could be high risk but incredibly rare. And we still have to consider all of these possibilities that happen. So I mentioned before about the hydraulic tube facility and how we could hypothetically put in 9 targets, but this is actually an example of where we've had to consider these different points. This specific target design is called a finned rabbit, and that's to help with flow issues. If we put 9 cylinder rabbits, they're just slick rabbits, they don't have the fins on them. If we put 9 of those within the tube, they generally jam up against each other and our flow drops, and we actually cannot run the reactor if the flow drops that much. So we have these finned capsules to kind of help with that. And so the hydraulic tube has some extra limitations on it that we have to consider. Okay. So what are the types of experiments that we work with, or what collaborations do I work with? So one of the big things that I specifically work with involves the National Isotope Development Center and the Isotope Program for the US Department of Energy. And they do a lot of experiments in our flux trap that involve medical isotope research and production. So for example, these are just a few of the radioisotopes that we've produced at Oak Ridge, and some of them are even ones that we have in the reactor right now running to make. So for example, we can take radium-226 targets and those capture a neutron, then decay into actinium-227. And they can use that as a cow in order to get radium-223, which is used in Xofigo, an FDA-approved method for fighting prostate cancer. So that's something that we do. And that's actually something that we do in the hydraulic tube because they're limited to 14 days. After 14 days, they can't really get anything more out and they really want to process things as fast as possible. So we pull them out and send them off. Lutetium-177, that's generated from ytterbium-176 and neutron capture, and that's used in neuroendocrine types of cancer. Strontium-89 is from neutron capture with strontium-88, and that's used in pain relief for bone cancer, specifically because strontium acts like calcium. So as calcium is taken up in active bone growth, such as cancerous cells, the strontium can be taken up instead, and that targets the area with the out-of-control growth. Irradium-192 is used as a radiation source in brachytherapy or targeted therapy where like a seed of radioactive material is placed near the cancerous tumor. Tungsten-188 is actually really interesting. That's from tungsten-186 picking up two neutrons, and it beta decays and gives off gamma rays which penetrate tumors and can be used for liver cancer or brachytherapy for invasive non-melanoma skin cancer. But there's some research into it for pancreatic cancer by coating Listeria bacteria with antibodies that contain this radiation source. And normally the human body can fight off that bacteria fairly easily, but if you have cancer and a suppressed immune system, the bacteria could sneak through, and carrying that radioactive source can help kill the cancer. So this is another thing. I'm not pre-med anymore. I mentioned at the beginning of the talk that biology wasn't really interesting to me, but you know, a lot of the bio stuff still comes back for this kind of thing. And this just sounds pretty cool in general, even if I'm not interested in the rest of biology. And these are just a few of the isotopes we've made in the past. There's quite a bit more. And so I work with a lot of people on these kinds of projects through the Department of Energy and through a group that we have here at Oak Ridge for the isotope program. There are also a lot of non-medical uses for isotopes we can produce. Oak Ridge is very, very proud of this. Berkelium-249 was a target used for heavy element research. Specifically, it was a target for the discovery of element 117. They took the berkelium target and slammed calcium-48 beams into it in order to produce just a handful of these element 117 nuclei, which eventually were named tennessine. And so they are very proud of this. This was done before I came down here, but people still talk about it. They probably will talk about it decades from now. Californium-252 is a neutron source that's used in reactor startup. It's also used to help detect impurities in coal, and the construction industry uses it for impurities in cement for detectors. It's also used to calibrate radiation detection instruments, including stuff used for like port security operations. HFIR supplies something like 70% of the world's demand. And one of those people that I network with at an earlier conference during graduate school was Julie Easold, and she heads up the Californium-252 program. So all of these people that you're meeting now are going to show up in your future. Nickel 63 is used as a national security application and detection for explosives and drugs at airports. Specifically, it's used in electron capture detector, which utilizes the electrons from the nickel 63, and it ejects electrons into the air. And then when an electron capturing compound, such as an explosive, is present, the detector notes a change. So it's able to say like, hey, check this out further. And then selenium 75 is used for gamma radiography, and it's used to inspect welds and look at steel thickness. And these are all part of the isotope program as well. And so this is the main group that I deal with and trying to get their experiments into the reactor and approved. Another thing the lab is very proud of is the work in plutonium-238 production. So there's a lot of NASA missions that require this plutonium fuel. And previously, the US stockpile from Savannah River was enough, but it's been decaying away and they're running out. And there's some thought that we need to produce 1 to 2 kilograms per year in order to meet their demand. And so the lab takes neptunium oxide, a different group, not my group, a group at the lab will take the neptunium oxide, mix it with aluminum and press it into pellets. And then at HFIR, we take those pellets and irradiate them for 2 to 3 cycles. And then we ship them off and they can process and separate the plutonium and ship it to LANL. And that's not part of the isotope program. It's an interesting distinction where the plutonium is actually a separate thing. That's not the isotope program, even though it is isotope production. One of those weird quirks. The other group that I work with a lot involves the materials group here. So because we provide such a high neutron damage environment, we can test the hardiness of different kinds of materials in these environments. So for example, we can look into accident tolerance of nuclear power reactor fuel. And at what point does something crack? HFIR was also used to study different potential materials for the first wall of the International Thermonuclear Experimental Reactor. And it's been used to look at the helium generation of materials like steel through neutron alpha reactions. So there's another group at Oak Ridge that does a lot of these materials things, and they further collaborate in networks with outside companies, trying to figure out what they need to see for their products and whether they can last under these high irradiation environments. That's kind of a sample of the influx stuff that we do. So once we get done with these targets, we have to inspect them. This is one of my occasional bay visits that I get to do, and see if there's any interesting markings on the target. So if something got jammed up against each other, and it hasn't happened to me yet. I've only been here for 2 years, but is there some kind of like bubbles forming that could indicate leakage, and we have to go in and inspect those kinds of things. But if everything is good, we work with shipping in order to send off the targets. This is just a photo of one of our casts that we have on site. And sometimes we have to store the targets for a while for byproducts to decay off, or they're just really high and their hot cells are not capable of taking it yet, or their hot cells do not have the space for us, and so we have to store them temporarily. But we always work with them in order to make sure that they get it when they want it as much as we can allow. So once we're done with a cycle, we defuel. And so these are like a series of pictures showing us defueling. And eventually it gets shipped off. But before we ship it off, we're big into the reuse program. And we use spent fuel for our gamma facility. So our gamma facility uses the spent fuel in order to provide a very high gamma environment in order to test materials. So on the HFIR side of things, on the reactor side of things for InVessel, we can provide a really high neutron flux. But afterwards, with the spent fuel, we can really provide a really high gamma flux. And so there's lots of uses for that. So different kind of capabilities that we do. We can look at, the samples can be subjected to gamma fluxes of up to 108 rad per hour. And that depends on the kind of fuel sample we use. We can use older fuel elements in order to have a lower flux environment, or we can have really high, and we can swap out high ones in order to make sure that they have this high environment going on the entire time. We have sweep gases that help control the environment, and we can even run cables down for data acquisition and power for the sample, depending on what they're doing. And it's a very similar process to our authorization for these InVessel experiments, so I won't bring the chart back, But this is usually more hands-on for us, and I get to spend a lot of time out in the bay. So it's another opportunity to get dressed up. And it also means that setup and procedural work for carrying out these experiments kind of takes a bigger role. You know, with the flux trap, everything's in the pool, and it's fairly routine, and we're very used to running those kinds of things. But with these, we don't run as often, and experiment setup can actually vary a bit. And it's not always as simple as dropping the sample into the center of the fuel, a spent fuel, and going on your merry way, especially if they have all these cables and sweep gas and instrumented capabilities. And we might be patching into different kinds of panels. And as boring as this sounds, you have to take into account cables that are draped across the floor because it's a safety hazard. So we primarily use it in order to qualify materials and components for the nuclear industry, and to help understand different kind of material behaviors in a radiation environment. So some examples involve resin radiation tolerance studies that are used in reactors. How does the resin act? People will investigate radiation resistance of materials for lunar environments. So for NASA again, and just all kinds of different groups will come in for this. And this involves a lot of collaboration with people outside of Oak Ridge. There are other groups that will come in from outside of the lab or in the lab, and not involved in the isotope or the materials program, and they will want to test something in this environment. As if this isn't enough for one person to deal with, there's always more work to do. And this is more examples of like your past coming back to haunt you. So because I worked at a nuclear power plant, I was put on our local nuclear safety culture panel, which is made up of power plant industry professionals. And we surveyed employees to see how they felt, like it was how safe they felt working in HFIR. And the our panel also looks at like accidents that happen at other reactors in order to make sure that the same kinds of things don't happen at HFIR. Because I worked with detectors during graduate school, I ended up involved in a gamma scanning project, which took a gamma detector and sealed it in a vessel that we could swim underwater. And some of the people I worked with on this project were people that I met at the Exotic Beam Summer School back in 2014 while I was in graduate school. And then because I'm a chemist, of all things, and I actually worked on water quality a little bit while I was an undergraduate, I was put on a team to figure out this issue that we had with some water samples from our filtration systems. So the past will always come back to you in one way or another. So just a final word, I always like to hammer on the idea that anything done in science is a collaborative effort. We build on what came from before, and we rely on others in order to carry out our work. Running an experiment at HFIR involves operators to run the reactor, researchers to propose ideas, maintenance in order to keep things running, people to actually build and process these targets, safety personnel like me to make sure that we don't blow anything up. And I am just a tiny part of an experiment work for these InVessel and gamma facilities, which is just a small amount of work done at HFIR, which is just one part of the overall lab at ORNL. So if you're interested in this or in any other work that we might be doing at the lab, because there's so much going on, please check out the job link here and see what's available. I know my group doesn't have anything posted right now, but I know some of the collaborators that I work with do. There's always something. So, and with that, I will end. That's my email address in case you want to contact me, and I'm happy to take any questions.
Okay, thank you very much for that excellent talk. And folks, feel free to send Krystin a digital clap. You can find that in your reaction buttons on Zoom. And so, Krystin, you should be able to see them showing up.
Oh, that's neat. I don't deal with Zoom here. We have Microsoft Teams in case anyone is curious.
So yeah, let's open it up to questions. Who wants to go first? And while we're waiting for folks to find their unmute button, I'll go first real quick.
Yeah.
Can you give us an idea about what percentage of those irradiation spots in the reactor are actually full for any given run cycle?
Yeah, so within the Beryllium Reflector, about half of those currently have, and so I say this from experience of 2 years, so I don't know like anything from the 80s, sorry. But so for recent history, about half of the beryllium spaces are taken up. with most of them are plutonium production targets. We're actually going to be increasing our plutonium production as time goes on for NASA. And as part of the Beryllium Reflector design, redo that we're doing in 2024, we're actually going to be opening up the Beryllium Reflector in order to have more spaces for plutonium production because it's a big deal. So about half of those are taken up right now based on their ability to produce targets and the kind of specific locations that they want within it. Within the flux trap itself, what did I say? That there were the 31 individual target holders and then 6 PTPs. And each of those can hold like 9 targets. It's probably around a quarter to a third full at any given time. No one wants the positions that are like at the ends, the very edges of the core. They all want them at the very center for some reason. I wonder why that is. So, you know, we have some stuff out at the end, but for the most part, it's like in the central positions. And not all of our holders have targets in them. That was part of the target holder design. We are actually out of current holders to use because we keep, they're not cheap to replace currently. And we want to make them cheaper to replace so that we can actually make them and replace them as soon as possible. And so it kind of just depends on the area. But yeah, I would say about a third of our flux trap is filled and about half of the Beryllium Reflector is. I don't know about neutron scattering, they're on their own. I think that's every day.
No, very good, thanks.
Yeah.
Dave, I see your hand up.
Yeah, hi. That's really interesting because I've heard about this place, but never knew any of the details. Way back when I put things in reactors, people were very concerned about what was really going in. And and then also you have a lot of locations.
Mm-hmm.
So, I mean, the samples must interact with one another, or at least interact with the neutron flux. Do you have to, I mean, what do you do about those kinds of problems?
So the samples themselves are encapsulated within these the rabbit capsules. And so we do not have them interact with each other. So experiment A can't really interact with experiment B, except when the capsules jam up against each other. And that's where that gets to that target design issue I talked about, where we have to make sure that they aren't, you know, crushing into each other to break them open. So from like a physical standpoint or a chemical standpoint, they won't do that. Now for like the neutron poison problems with the absorbers, that kind of stuff, we have to, it's basically a group discussion of can we afford to put these neutron absorbers in that will affect all of the surrounding targets. And so, you know, that would involve a collaborative, like I said, a collaborative discussion of like, okay, so who can stand to be near this? Can any of you stand to be near this, or do you all say no to this? And it hasn't come up very often while I've been here, but it is something that will probably be coming up in the future. And so we just kind of have to consider all of the possibilities. Usually we try to avoid neutron absorbers as much as possible just because of the cycle problems that they present, especially for neutron scattering, because the neutron scattering is such an issue. But yeah, we basically have, before every cycle, I have this Duke It Out meeting with anyone who wants to put things into the reactor. And we go over any of the problems that they might have in being near certain other things and what spaces they're capable of taking. And it's like anywhere between half an hour to 3 hours long of just discussing all of the possibilities. And I come in with like, okay, well, I can put you guys here, or I can put you guys here, or I can put you guys here. And there's just a bunch of possibilities that we come up with.
Okay, yeah, thanks.
Yeah.
Okay, Daniel, I see your hand up.
Hi, excellent talk, and it's very nice to see you again, Krystin.
Hi.
In regards to the work that you're doing, one thing that you had said that caught my attention was that the fuel that you're working with is high enriched uranium, enriched up to around 90%. And it's kind of a two-part question. The first part is, are there plans for ORNL to eventually convert to a low enriched uranium research reactor? And then the second question is, what kind of safety considerations do you have to take into account since you're dealing with such higher levels of enrichment, which means that things like it could be easier if you just had 2 rods next to each other to achieve criticality comparatively to LEU rods. So what are those extra safety considerations you have to take into account when handling HEU?
Yeah, okay, so for the first part of the question, actually, yes, there is a lot of work and consideration going into going to a low enriched uranium fuel instead. That is a very long-term process. I mentioned before about the Beryllium Reflector outage that we're going to be having in 2024. And so this would take place past that point, like way past that point. So there's already discussions into that because ideally we would like to switch to low just for like the security issues that come up into play. So there are plans. I'm not involved in that team, so I can't really like tell you anything super cool and interesting about it, but they are trying to do that. Because I'm not a fuel engineer. But the second part of your question with the kind of like the safety and different kind of controls that we have to do. So I mentioned before how we have inner and outer fuel elements. We actually keep them separate within the storage up to a certain point. So when we pull them out right away, we just put them in separate storage locations. We don't put them next to each other just to like try to prevent that kind of issue from happening. We also, as far as like the security aspect, there's a lot of like restrictions on what people can know and shipping, for example, like all the photos that I showed you guys, like they're all things that have been cleared and are either public at this point, or I had to get special permission for it. So there's like certain things that we can't, like, we just don't discuss about. But yeah, so hopefully a lot of that will go away with lower enriched, thing in 30 years or however long the time scale is for that.
Okay.
Well, thank you.
So does anybody else have any last quick question? Because we're almost at 2 o'clock right now.
Something else and you don't feel comfortable in sharing with the group, or you have question about my pathway or jobs at Oak Ridge or anything else, you can feel free to email me. Make sure the I goes before the E. That's a big deal.
Okay, last chance, folks. Okay, if not, well, thank you very much again, Krystin. That was an excellent talk. I really enjoyed it.
I'm glad to be here and talk to all the current NSSC crew and everyone else.
And with that, I think we're all done here.
All right. Well, happy Wednesday, everyone.
Have a good day, everyone.
Thank you.
Bye.
Bye.